Today we're going to be going into detail about the hard-to-handle rocket, the rocket that I launched in the Fisher Funds ad. This rocket that we built is called Hard to Handle. The goals were to get level 1 certification and to be a supersonic rocket, but also to get the eye height record for the New Zealand Rocketry Association. The rocket went supersonic, which was decent, and it went 9,288 feet high, with it going Mach 1.14. It pulled 30 Gs, and it has a 40 millimeter diameter, and it is 1 meter long. This rocket was designed in a program called Open Rocket. However, most of the parts were made in Fusion 360 and printed on a 3D printer. Next, we're going to talk about our innovations that we made. See what you think of them. For Element 1, the rocket was designed around a 38mm DMS engine. This was for maximum aerodynamic efficiency. The carbon fiber tube is 1 millimeter thick. From that moment on, that makes the entire rocket custom built. For element number 2, the rocket was dual head-end deployed. This means that there isn't a split in the middle. Instead, all of the weight is up the top, which is perfect for height records. We had to define our own tail to nose weight ratio to make it work. For element number 3, the rocket is aerodynamically efficient because it has no lugs. This means that we had to design our own launch rail. For element number 4, we have the nose cone. This took a long time to design. It must sit straight on the rocket so that the rocket doesn't veer off course. It's also thin and lightweight. It's printed out of ABS instead of PLA because the rocket goes supersonic, which means there's lots of heat generated at the top of the rocket. This also has to encapsulate the entire parachute. So this has to fit into there. And it has in-print hardware. So we have a nut and a washer in the top to hold the shock cord. This shock cord holds the parachute on tight. We also have no shear pins, and the tolerancing needs to be perfect. For element number 5, we have the fins. They are optimized and designed in Open Rocket. The stability was also 2 to 3 depending on what engine you use. To get the fins straight, we created a fin jig for sub-millimeter accuracy. While cutting the fins, we also stacked them so that they're the exact same cut. This created a very efficient and straight rocket. For element number 6, we have the Altimeter Bay. There was a lot of innovations going into this. For starters, we tried to save weight using the CF tube. We really wanted to use it because it was so much lighter, but the problem was the telemetry couldn't get through back to the ground. We also tried carbon fiber rods. We tried tapping and dyeing them, but the carbon fiber crumbled. After that, we tried E-clips, but it wasn't practical and it lost signal and it was too hard to work with. Space was absolutely critical in a 40mm airframe. There was so little amount of space and we had to fit lots of stuff inside of it. For this, we created a custom 3D printed sled which housed the altimeter and a battery. It also had the switch on a side. The altimeter was an Altus Metrum Telemini V3. In summary, the entire rocket was weight optimized for a height record. Because of this, we made the tube as small as possible. We also have a very slim nose cone, and the baffles are made out of carbon fiber so that they're lightweight. We also have a tiny altimeter. From all of this, we got over 2.8 kilometers, and we want to go even higher with a better engine.
Thanks for watching this video, and see you in the next one.